Interesting talks, thematically aligned with what the title says, HPC programming. And again, the first talk will be given by Kirshanthan, Sundararajah, and several others to follow. I'll be chairing this session. Okay, so Kirshanthan, whenever you are ready. Yeah.
Hi everyone. Room seems to be sparse. My talk is about sparse tensors, so it fits the theme, I guess.
Everybody in the front row.
So today I'm going to talk about vectorizing sparse coiteration. This work is mainly done by my student Kabilan. Unfortunately, he's not able to be here at this moment, so I'll be presenting his work. So before getting to, we all understand the importance of array programming. So I'm going to start this talk with how the code gets generated for array programs. So let's take our very favorite example, matrix multiplication. So I have given the matrix multiplication A is equal B times C in terms of Einstein notation over here. So let's assume that all of these matrices are dense. This is our favorite example, HPC 101. How do we generate the code for this example? It's just simple 3D nested loop. I want you to pay attention to the innermost nested loop. So this is the dimension of matrices B and C that gets contracted. So it's a very simple for loop that runs k from 0 to k, and you perform the computation inside it. So this is your dense matrix multiplication, and this is from a 10,000 feet point of view, because we know how for a long time people have been optimizing this code, and it's pretty mature now. So let's take the case where these matrices are somewhat sparse. So now, since there are more zeros in this matrix, we can represent them in compressed format. So in this case, I'm going to represent B in CSR, compressed sparse row format. So the rows get compressed here, and this matrix C in CSE, so the columns get compressed column format, so the columns get compressed. So now let's think about how the code for the same kernel gets generated. So now we have a lot of sparse tensor compilers, and one of the abstractions that they use is iteration graph. So I have provided a partial iteration graph over there, and that iteration graph nodes are basically your indices, and the edges are basically the dimensions of your tensors. So since the B10 or B matrix get compressed along the rows, the first dimension of the matrix is a dense dimension, and the second dimension is basically sparse. So the second dimension kind of depends on the first dimension, and the same way for the matrix C, second dimension is dense and the first dimension is sparse. So it gets the second dimension depends on the first dimension, and you have your index k, and if you look at the dimensions that get incident on the k node, the second dimension of B and the first dimension of C, both of them are sparse. So how do we generate code for this? We have still that two for loops, outer for loops I and j, but let's look at the inner loop. So now you have to contract these two dimensions of B and C, but it's a little more complex than the simple for loop in your dense matrix multiplication. So now this is what we call a two-finger loop. If you have you might have encountered this if you have written some sort of a merge program. or like, a merge part of the merge sort. And now you have to walk through these two compressed arrays, and you have to update those pointers, and whenever the indices becomes equal, then only you get to perform the computation. Okay, and then you have to appropriately advance the pointers as well. So both of them are essentially doing the same computation, which is matrix-matrix multiplication, but the sparse matrix multiplication becomes much more complex. So now let's think about a particular optimization, which is vectorizing this inner loop. It's very simple to vectorize the dense computation, because what you have to do is like you run your either loop vectorizer on the inner loop, or you can basically chunk this inner loop into, unroll this inner loop by a factor, and then you run your SLP vectorizer, it'll get vectorized, and this is pretty common. Your general purpose compilers can even do this. But essentially we are doing the same computation on the sparse tensors or sparse matrices, but this loop is not get vectorized as easily as the dense one. So what are the reasons? We have loop carry dependencies, data dependent branches are there, and you see like non-affine point iterations are there, and everything bad you can say about this loop is there. So your loop won't get vectorized. So now let's see like how we can vectorize this manually. Okay, so in order to manually vectorize this loop, we want to chunk these iterations, like we want to chunk this inner loop iterations into smaller pieces. Okay, so I'm going to keep the outer for loops as it is, and there are few phases. That means I have to load the data, and then I have to perform the computation based on some condition, and then I have to advance the pointers, but that you have to do all this for a chunk of data. So let's assume that we can do for some factor, 4, 8, whatever. And now the condition, the loop termination condition also going to be different, and that condition will be something of sort of jumping every n iterations. So we can do all these things and get that loop chunked, and still I didn't answer how do we vectorize this loop. Okay, so if we did this, let's assume that your matrix, in some rows you have less than n number of elements. What will happen? You will skip some rows, right? So what I'm going to do is like I'm going to keep the original loop as it is, and the loop that I want to vectorize, I keep it, both the versions, I keep these things. So if the condition C fails, it's going to fall back to the slower version that you have written. Okay, so I'm going to call it the first version as SIMD fast lane, and the second version as SIMD, or scalar version as SIMD slow lane. So now, how do we vectorize each of these phases that I have talked about? So initially what I want to do is I want to load a chunk. So the chunk size is basically 4. I want to load 4 elements, and what I'm going to do is that like I only going to perform this computation when the indices matches, right? So I'm going to broadcast these indices to vector lanes, and I'm going to compare against with the indices of matrix C, and I'm going to create a mask, vector mask. And then based on that vector mask, I'm going to filter the elements of C, and then I can perform a reduction, and I'll get only the elements where the computation should be realized. And I can then pack them together into vector lanes, and then I'm going to take the already packed values of B, and then I'm going to perform an element-wise multiplication, and finally I can perform a reduction. So you can see all these operations can be done with vector instructions. Okay. So is this the only thing that we should supposed to do? No, we have to perform pointer advancement. So how do we perform pointer advancement? So you have a bunch of column and row indices, and what I'm going to do is like I'm going to take the maximum row index and the maximum column index of all of the chunks, and I'm going to take the minimum of those things so that I can prepare for the next iteration. So you can do the same thing with vectorized instructions as well. So how am I going to do this? Again, I have my pivot for the maximum element of B. Then I'm going to compare against with all the column indices and row indices of C. Again, I'm going to get a mask. I'm going to perform a reduction, and then this will tell me by what element or what offset I should increase the pointers for each of these running pointers, or your two fingers. Okay. So again, this is fully vectorized computation. Or you can say, I haven't implemented, like we'll see how we're going to implement this, but this is like conceptually a vectorized computation. So there's no branches, no ugly dependencies. It's a fully vectorized computation. So we have three stages. You have to load the data, you have to perform the computation, and you have to advance the pointers. All of these things can be done with vector instructions, or you can, these are chunks, you can do it with the scalar instructions as well. So how do we implement this? The implementation is very interesting. So we implement this with the MLIR pass. So you might already know that we have a sparse tensor dialect, and there's a very modular compiler called sparsification compiler, which takes both sparse tensor programs written with both sparse tensor dialect and linear algebra dialect, and the loops in the sparse tensor dialect, if they are fully sparse loops or coiteration loops, they will get lowered to structured control flow loops. And linear algebra loops, they are regular loops, so you can directly lower it down to vector dialect. So they are readily vectorized, and the sparse coiterations loops won't get vectorized. They are they are in SCF form. So what did we do here is that we implement this vectorization strategy that I have been explaining so far into a pass that will take these structured control flow loops and turn it into vector instructions or vector IR instructions. And once it does its job, then you don't have to do anything, because the lowering of vector instructions to LLVM dialect and then LLVM IR is already built for us. Okay, so the interesting part about this implementation is that you can make, like, each of the stages that I mentioned, you can configure them as, do you want to perform it with vector instructions or scalar instructions? If you want to perform it with vector instructions, you have to invoke our pass and turn SCF loops into vector instruction or vector dialect. If you don't want that, you can just directly lower it using the SCF loops. So we have implemented this setup on a Intel Xeon Gold Sapphire Rapids, which has AVX512 support. And what we have done is that, like, we have taken, so for example, the kernel that I was explaining earlier, SpGEMM, and we have three stages: data loading, then performing the computation, and finally pointer advancement. We have tried all different combinations. Okay, so we can keep it like everything is scalar, or everything is vector, or some of them are scalar and vector. So we found that the most profitable version was like the data loading should be done using vector instructions, and all the others should be done with scaling instructions. So that is the one that gives you the highest speed up, which is like 2.77x than the original version. And then we did a little bit of ablation study. So remember, I have talked about a vector width, right? Like conceptually, you can chunk this together by n, and this n could be anything. So in our case, we tried with different vector widths. So we tried 2, 4, 8, and 16, and with varying sparsity, we found that the one with vector width 4 is the best performing version. So there are many tunable knobs here. One thing is that you can tune the different faces to be vector or scalar, or you can also tune the vector width as well. And there are many reasons for it. For example, if you leave it as scalar operations, it can take advantage of instruction level parallelism. And if you use it with vector instruction, you might, sometimes the vector gather and scatter can break your performance. And also, this depends on how many masking, or to do the masking, how many the resources, like register resources, should be available there. So, and we have implemented this thing on synthetic data with multiple different kernels, and you can see all of the kernels can be written in INSUM notation here, and we get a good speed up for the same configuration that I mentioned, like first phase is vector and the other phases are scalar. Then we also vary the sparsity, so we varied from almost 0.01 to up to 10%. 10% is not that practical because 10% means not so sparse. Generally, sparse tensors are like around like less than 1%. And you can see compared to the baseline version, the vectorized version is performing much better. In addition to that, so now you have you can exploit the outer loop parallelism as well. So we have done some outer loop parallelism, and with different parallel elements, it is scaling well. So, and also when we did this experiment with real world tensor data, it is it gives you moderate speed up, but we didn't see any regression as well. So ultimately, what we have done here is that we have a very good SIMD vectorization strategy for sparse tensor coiterations, and we have a geometric speed up of 2.39 and almost no speed up regression on real world data. And the speed up is scalable on multicore. That's all I have for you today, and please ask questions.
We have time for one or maybe two quick questions. Yeah, Tyler.
Hey, thanks. Great talk. I was wondering, kind of, when you were doing the uniform sparsity and you went to like the real world sparsity, I saw some of the data sets and it looked like they might have been like power law style data sets, and then you get a lot of like irregularity. Like sometimes some things are more dense and some things are more sparse.
Yes.
Like, do you think you could adapt to that?
Yes. So that's why I have like a fast lane and the slow lane.
Okay.
So if your sparsity is not that much, if some of the parts are extremely sparse, you can use your scalar version of the code.
Yeah.
So that's how it gets adapted. So you don't have to perform anything special because we have both versions in the generated code.
But I guess you have a knob that you say like how sparse does it have to be to go down either branch?
Yes.
Yeah.
Yes. Yeah.
Okay. Very cool.
So the vector width actually controls it. Yeah.
Cool.
Thank you. In the interest of time, we'll go on to the next talk given by. Sorry, I didn't get.